Hi, my name is Vivek, and today I'm going to talk about the cone of silence, which is a new approach to speech separation and localization. This is joint work with my colleagues Tarapat, Steve, and Ira, and we are from the University of Washington. First, let's take a look at a short example of what our method can do in the wild. Suppose we have a scenario like this, where we have four people sitting around a table talking at the same time. At the center of the table is a small microphone array. Let's hear what it sounds like.
Have you tasted the
Orange
banana
versus
with
red.
the
Where do
rind?
you
It
stand
is
on the
delicious.
whole
Just
orange
bite
versus
into the
red
lemon
debate?
and eat the lemon as
No,
is.
No, I
orange is
think
when you
that
think of
red
delicious.
Our method can separate and localize each speaker, allowing us to listen to a specific one. Let's hear what the person on the left sounds like. So, orange versus red. Where do you stand on the whole orange versus red debate? No, I think that red definitely a better color. Okay. We'll also show more demos towards the end of the video. Formally, we can define the problem as follows. Suppose we have an M-channel microphone array and N speakers. We have an observed mixture M, which has T samples for each of the M microphones. We assume this mixture M is a sum of the different speech signals Si, along with some background which we would like to ignore completely. Our goal then is to recover the speech signals as well as the angular locations of the different speakers. There have been many approaches over the years that address this kind of problem. Beamforming is one such approach, which is a signal processing technique. Beamforming typically uses phase information as well as trigonometry or linear subspaces to separate and isolate sources. Recently, deep learning has also shown promise. In contrast to beamforming, deep learning typically learns the spatial and source information, and it does so by leveraging large amounts of training data. Our method uses the best of both worlds, where we have a deep network that can learn a rich feature representation, but we also use ideas from beamforming to explicitly inform the network about aspects of the world geometry. Let's see how it works. At a high level, our method is a binary search approach. Imagine we have some speakers at some locations as shown in this diagram. The goal is to exponentially decrease the search space in order to separate and localize all of the sources. We have a network that performs region-based source separation, which means that we can isolate sources of interest coming from various regions of space. In this first step here, we are running quadrant-based separation, or regions of 90 degrees, and we can see immediately that two of the quadrants have no output signal from the network. We can discard them immediately and recurse and subdivide on the remaining regions, until finally we can separate and localize all speakers to 2 degrees accuracy. Some of the advantages of our approach is that it is more general than existing methods, and we also show state-of-the-art results for both localization and separation when compared to a number of recent baselines. By region-based source separation, we mean that we would like to separate sources based on their angular direction of arrival. Suppose we have some target angle theta. We would like to hear sources that come from this angle theta and not hear anything else. In our case, we also have a second parameter, W, corresponding to a window size, meaning that we would like to hear sources coming from this region, theta plus or minus W over 2, and not hear anything else. Because this region is a cone, we call this the cone of silence. This is a reference to the cone of silence from the TV show Get Smart. How do we build a network with this cone of silence property? Our network is based on the DMUX and a UNet-style architecture, where we have a series of encoder and decoder blocks as well as skip connections. Separation based on theta is provided by modifying the input in a conditional way. And for W, we use a one-hot conditioning vector H. These two parameters are seen here in orange and fed into the network with the orange arrows. Let's first look at this modified input and the target angle theta. We use the idea of time delays, which is a phenomenon seen in multi-microphone recordings. Suppose we have some microphones in the environment and a speaker coming from an angle theta. If we look at the signals captured by the microphones, we'll notice that they are shifted copies of one another. And furthermore, this shift only depends on the angle of the speaker theta. If we know theta, we can calculate this shift in a closed form way. If we would then like to isolate sources coming from theta, what we can do is undo the time delays in the mixture and then feed it into the network. So if the input mixture looks like this, then we can shift microphone 2 by this time delay delta t theta so that the signals are now temporally aligned across the different microphones. We can then train a network that only outputs signals that are temporally aligned in the mixture and ignore everything else. More concretely, if we fed the original mixture into the network, it would output silence because the signals are not aligned across time. But if we shifted microphone 2 by delta t theta and then fed it into the network, it would output the signal because it is aligned across time. The key idea here is that the network can do this separation even in the presence of background sounds or sources which come from different angles because they have different time delays and are not aligned across time. This is the same idea as a delay and sum beamformer, except the sum step is replaced by a deep network. Let's now look at the window size. We use a one-hot encoded vector h corresponding to a discrete number of possible window sizes. This is inspired by the WaveNet global conditioning framework. H is fed into every encoder and decoder block, and it goes through a learned linear upsampling before being fused with the rest of the information. That's it for how we create the network that has this cone of silence property. In the rest of the talk, I'll give it to my colleague Mek, who will walk you through some of the demos and experimental results from our paper.
Thank you, Vivek. To understand more about how proposed method works, let's look at the network output on each step of the algorithm in more details. Suppose we have 4 speakers at some locations as shown on the left. Now let's hear the input mixture.
There's a story.
Here again, they were denied October the following year.
We first run the separation network on each quadrant. Let's hear what's happening in the top left quadrant and the bottom left quadrant. You can play with this interactive visualization on our project website. For the top left quadrant, we expect to hear one voice.
Here again, they were denied a voice.
And for the bottom left quadrant, we expect to hear 3 voices.
There's a story.
Completion is expected by October the following year.
For other regions, we hear empty signals. Moving to the next step. Because the top right and bottom right quadrants are empty, we remove them from the consideration. Next, we subdivide the top left quadrant and bottom left quadrant into 4 regions. One highlight I want to show you here is the green region. Although there is no voice in this region, we hear speaker 1 from the yellow region because the speaker is very close to the borderline. Then we further subdivide our angular regions from the previous steps. We note here that we didn't remove any region from the consideration, and we will talk more about this later in the presentation. Next step. And here's what it looks like on the final step. Let's focus here on the top left regions. We have 6 location candidates for speaker 1, where most of them sound very similar to one another. Similarly, we have many location candidates for other speakers as well. To eliminate this problem, we run non-maxima suppression on these candidates to only get the signal with the highest energy. After running non-maxima suppression, here's what we get. From our experiment, we found that using low cutoff threshold for empty signals to get as many location candidates as possible is better than using high cutoff threshold. And this is because high cutoff threshold for empty signals leads to many false negatives that we have failed to localize. Here we show the performance of our network on different window sizes. For sources within the specified angular region, we see that the signal to noise ratio improvement is very high, up to 15 dB on average, and very low outside the regions. At the borderline regions, the signal to noise ratio improvement is increasing, indicating the reason why there's a signal leakage into consecutive regions as we have seen earlier. Here we show the separation performance compared to many baselines that operate on 2 different domains, waveform and spectrogram. Our method shows state-of-the-art separation performance. Now let's hear the separation performance with baselines. In this example, we have a scene with 2 speakers. Again, for more audio samples, please visit our project website.
We also need a small plastic snake. It was a management problem in the hospital. 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 We also need a small plastic snake and a. We also need a small plastic snake and a. We also need a small plastic snake and a. We also need a small plastic snake and a.
Then we look at the localization performance. We compared our method with many baselines, including traditional signal processing and recent deep learning-based methods. We found that all baselines have troubles in the presence of high background noise. We also show the performance of our network on datasets with up to 8 speakers. One important note here is that the network generalizes very well to high number of speakers. In this experiment, we trained a network using only up to 4 speakers per scene. We found that the network can handle up to 8 speakers. Now moving to the performance of our method in real-world scenarios. Here we show 2 demos, moving speakers and loud background noise.
Of modern linguistics, one of the founders of the field of cognitive science, and perhaps the most avidly read political theorist and commentator of modern linguistics. One of the founders of the field of cognitive science, and perhaps the most avidly read political theorist and commentator.
16 hours right now. I have to wait until I work in here 40 hours to rack up another single.
So this is a recording test. I'm trying to do a video call right now, and one person in the house is using the blender, and another person is vacuuming right behind me. This is the kind of scenario which one might experience when trying to take calls while working from home. So this is a recording test. I'm trying to do a video call right now, and one person in the house is using the blender, and another person is vacuuming right behind me. This is the kind of scenario which one might experience when trying to take calls while working from home.
Please visit our project website for code, more demos, and audio samples. Thank you.